So next, I'll be talking about a follow-on program to Ocular 4.0, which we're calling R-OTE, which stands for R-Code Occultation Timing Extractor. And this program has been solely programmed by Bob Anderson, a colleague of mine here in Oregon. And I've helped out with some beta testing and writing a user manual. I'll go through the program incrementally here, but the major advances over Ocular, we've been working on this actually for several years. And we started out with the idea that we should be using more powerful statistical testing, such as Bayesian statistics and that sort of thing. And in fact, Bob spent about a year working on a Bayesian solution to finding occultation signals. But what we found was that that wasn't necessary. And so we're going to share all of that learning with you in this presentation. So with R-OTE, some of the positive advances that we've made over our Ocular version was that R-OTE is a cross-platform program. It could be run in Windows, in Mac, or in Linux. Any system that will run our code can run R-OTE. Now, R-code is a very powerful statistical programming language, but it's a very high-level language, and it isn't like you'd be programming in C or something where you can control your user interface pretty easily. So we had to adopt a different user interface, and in this case we're using a web browser, and you can use either Google Chrome, Firefox, Safari, Fast Browser, which is one I just found, and currently Internet Explorer does not work, but there's enough other browsers that you can find something that will work. So that's one of the nice things. Ocular was strictly Windows programmed. R-OTE can work in several different environments. Now, another advance is that the method for finding occultation events uses maximum likelihood estimation. And what that does is it is a process for establishing the search parameters, or the parameters of the model against the actual data in the light curve. So in doing this, we've now made the disappearance and reappearance solutions are independently determined. In Ocular, they were linked by the duration of the event. Now the two events are entirely independent. By using the maximum likelihood estimation methods, R-OTE can also use another statistical model testing routine called IOTA information criteria, and I'll just refer to that as AIC. And what AIC can do is you can run different models against the same light curve and then compare them directly with a rating criteria, so to speak. So for example, we can compare a square wave solution against a gradual transition solution. Another major advance was we've implemented error confidence intervals now that are based on noise, signal to noise ratio, and noise symmetry, and I'll explain what those mean here in a little bit. We've added the estimation of stellar diameters and occultation limb angles, and that would be for events that have gradual transitions. And then for those events with gradual transitions, if you have enough data points, we can also test for stellar limb darkening models. And I'll cover that briefly today as well. We're introducing a new concept, which I'm going to call multiple solution reporting. It would introduce somewhat of a dilemma for IOTA, in that it means you might have more than one valid solution to a event disappearance or reappearance. We might talk about that. And another addition is that there's a routine in ROTE that will extract difficult to see events. In fact, you might not see the event in the light curve, and we can do that with 99.9% confidence, and I'll talk a little bit about that today as well, how we do that. And then this current version uses the maximum likelihood estimation and the AIC method to exclude false positive events. And this is pretty important because we can find events with high confidence, but up until now it's been hard to prove that those events aren't just spurious due to noise. And so we have a routine in here that will exclude spurious events, and I'll speak to that in a second as well. Some features that we put in, someone says sound is not working, but I think it's going out okay, so someone please confirm that you're getting sound okay. Okay. So special features that we added, you can import a light curve, and then you can trim it, you can detrend it, you can block integrate it. So we've made ROTE a little more powerful in handling the light curve. We've done a separate noise analysis that assures the data that we're analyzing is independent and identically distributed, which is necessary. We've added a multi-purpose synthetic light curve generator so that you can actually generate your own light curves, make them as tough as you want. You can put in straight lines and add noise and test against ROTE and do your own testing if you want. And then finally, we've added a grays analysis capability, which I'll demonstrate in a second. Okay, so these are the kind of light curves that ROTE is designed to analyze. And if this top one is what we would call a high signal to noise ratio square wave. And we wish all of our occultations looked just like this. That would be great. And in fact, these are somewhat trivial in that the observer can often just look at their video and pick the DNR times right off the video. These would be the best case. ROTE will analyze these. It will do subframe timing if the signal to noise ratio is high enough where that's a valid outcome. So this is a pretty straightforward event. But it will also do these low signal to noise ratio square wave events. And this is a pretty low signal to noise ratio light curve. There is an event in that light curve, and if you weren't really knowing what to look for, you might not find one. Well, ROTE will find these types of events. So I'll show you that in a second. And then lastly, we also can analyze high signal to noise ratio gradual transitions where the light drops gradually to an event bottom and then reappears gradually. And those would be light curves where the star has an appreciable angular diameter when occulted. So those are the three primary light curves that we have. So let's talk a little bit more about some of the details. The use of maximum likelihood estimation and the OTE information criterion for light curve fit and model selection. So how does an observer decide if the best solution to a light curve is a square wave or a gradual transition light curve? Up until now we've been using judgment. Even with ocular, we could fit a square wave or we could fit a gradual transition curve. We didn't have a way of deciding between those two. It was a matter of judgment of which looked best. So in ROTE, different light curve models have differing degrees of freedom. If we have a square wave model, we have 4 degrees of freedom. If we have a gradual transition light curve, we have 6 degrees of freedom. So if you're using a frequentist type program like ocular, the solution with the highest number of degrees of freedom is always going to fit your light curve better than the lower number of degrees of freedom, all other things being equal. So with ROTE, it solves this problem by using the AIC OTE information criterion as a way of rating the two models. The maximum likelihood estimation delivers repeatable model fit statistics in the form of a log likelihood number. And then the AIC compares the log likelihood of each model and adjusts that rating for each model based on the degrees of freedom in the model. And so now we can compare different models on an equal basis. In ROTE, we also compare square wave and gradual transition models against a straight line model. So particularly for the low signal to noise ratio light curves, we are comparing it to a straight line with just noise added to see if in fact the event might best, the model might best agree with a mist that just has noise in the baseline. So for an ROTE, excuse me, we're using AIC then as a rating for each model, and it gives us a percentage relative likelihood, and then the user can evaluate that, and I'll show you that. Okay, so here's an example of how we would evaluate the models against the light curve. So here is a light curve. You can see there's a very clear event there, and you might choose to fit a square wave to that event, which you could do, and ocular would do that, or you might choose to fit a gradual transition model to that event, and you could do that, and ocular would do that. But what we can do in ROTE that's different is we now have a maximum likelihood number for the square wave fit and a maximum likelihood number for the gradual transition model fit. And over here we see those numbers. Here's square wave. We have a minus 6.446 8.2. For the gradual transition, which we call edge on disk, it's a minus 6431.5. And of course, we can apply a straight line to that, which in this case would be trivial. We also have a number there. But we can compare these three numbers with AIC, and clearly it shows at a probability of 1.0 or 100% that the gradual transition or edge on disk model is the proper fit. Now I can confirm that to you because I prepared this light curve using the curve generator, and it in fact was a gradual transition light curve. So that's the kind of testing that you can do to verify that ROTE is actually working properly. Someone said activate your cursor, and I can't tell you how I would do that. Maybe somebody could tell me how to do that. Okay. So next, we want to talk about the noise, how ROTE handles noise. This is a new learning that we came up with. This is a new major feature in that the noise confidence intervals are now based on both the noise signal to noise ratio and noise symmetry. And this is a new term that we want you to become familiar with. So here's two representative light curves, and in this left light curve, the noise is very prominent in the baseline, but very low in the event bottom. And we see lots of events that look like this. When the light drops down, we have very low noise levels. We call this symmetry in that we do a ratio of the noise in the event bottom to the baseline, and this particular light curve would have a noise symmetry of 0.1. The right panel has noise in the baseline and in the event bottom that are very similar, and in fact this is a generated light curve, and the noise symmetry is actually 1.0, which means that the event bottom noise is exactly the same as the baseline noise. The learning from this is that when you have asymmetry, such as in the left light curve, then you have asymmetrical error bars. That is, your plus error bar is different than your minus error bar. And I'll just briefly explain why. And the reason is that the greater the noise coming into the disappearance, that higher noise level can affect where the disappearance occurs more than the low noise level can affect it. So once we get disappearance, our error bar is less than before we get the disappearance. Then we would reverse that on reappearance. The shape of these curves shows that the above line is the plus, the below line is the minus, and the x-axis is signal to noise ratio. So this would be 2, 4, 6, 8, 10. So we see that the plus or minus difference is not very high if the signal to noise ratio is high. But when we get into low signal to noise ratios, the plus to minus difference is almost 3 to 1. So noise symmetry is a new thing that's implemented in ROTE. On the right panel, we've plotted the error bars, and they are symmetrical because the symmetry is also symmetrical. And for high signal to noise ratios with high symmetry, we have very high error bars. And at the very low signal to noise ratios around 0.5, it's plus or minus 40 readings. Just to give you a comparison, over on the left panel at 0.5, the error bars are plus 1.5 to about 0.5. So the learning is that noise has a huge effect on error bars, and the symmetry of the noise has a huge effect on error bars. Now, Bob is still working on the error bar issue, and we expect that we'll have better estimates of error bars as we move forward, but right now what we have is very conservative and very workable to move forward. Okay, now I mentioned that we can estimate stellar diameters and occultation limb angles, and we do that by fitting an edge-on disk model or a gradual transition model to the light curve. So the right panel indicates a model fit, and the left panel shows the type of asteroid limb angles and star size that result in that model fit. So we can actually solve for stellar diameter. Here I have a stellar diameter that's 5 readings. We can also do that in milli-arc seconds if we put in the asteroid speed in arc seconds. And we can solve for the limb angles, and this would be the angle that we make to the line of sight, so that, or from a perpendicular to the line of sight, or to the line of motion, excuse me. So the disappearance limb angle here would be 1 degree, and the reappearance angle would be about 47 degrees. We can extrapolate this even further in that if we have a profile, as I can see down here in the right-hand corner, sometimes profiles will allow us to estimate fairly accurately the limb angle. So if we look at this asteroid profile on the left side here, we see a series of points which says that the limb angle there is pretty easy to estimate. If we can input that limb angle in as a known value, then we can further refine the star size, and so we have a nice procedure for being able to estimate star size. Okay, now when I'll just back up here again a little bit. The actual fit of the edge-on disk model to the light curve can be adjusted for limb darkening. Now it seems like that might be a pretty ambitious undertaking, but with the AIC model comparison, we have a valid way to do that. And in fact, we can generate synthetic light curves, add noise to them, and our finding has been that if we have a long enough transition with enough data points, say 15 to 20 data points in the transition, we can start to differentiate between limb darkening models. So this slide shows various limb darkening models. The left image is a linear law model. The middle image is a square root law model. And the right image is no limb darkening, just constant. And then the graphic at the bottom left corner shows how those models fall off with distance from the center of the star. With the and those are all labeled. So I'm not going to get into detail on those. You can read up on those in the literature if you're interested. The interesting thing is that we have that capability, and in the future we should even be able to add capability to sort out if there are star spots and things like that. Or maybe the star isn't circular. Maybe it has an irregular edge like Betelgeuse or something like that.